All right, one thing that I'm noticing is, just so we all know, tomorrow morning NanoHub will be down. It says 6 till 9 a.m., so it should be back up by time like normal work hours are, but there's a chance that it could run a little bit later into the day. I think it'll probably be back by tomorrow afternoon anyway, though. Cool. So we're here, last module. Well, I mean, there's module 5, but last required module, last required project. Looking at some linear algebra for finite element analysis. And this one's a truss structure, but really it's the same problem as like homework 1, as our first problem in homework 4. It's just now we have like a 2-dimensional stiffness matrix rather than just 1-dimensional. We're just getting started, like reading through. Okay. What is it? Oh, it's just loading. I didn't notice any issues when I first did it. Okay. I know I have to double check like which Wi-Fi I'm connected to. There's even like a lower bandwidth Wi-Fi and a higher one. I'd have to manually choose which one I want to be part of. So I'll give like a little tour since you're kind of just starting to look at it. They lock it now. Yeah. Like right now it got stuck open, but it gets locked. So quick tour. We are not. So finite element method has like 3 main steps. Like the first step is geometry, like defining geometry and assigning materials, and then the next step is like prescribe boundary conditions and solve it. And then the last step is like post-process. We're skipping all that like meshing part, the meshing and the material. I mean, we're kind of doing material property because we're setting what Young's modulus is, but we're not doing any of like the geometry building the mesh. It all gets, like everything that has to do with the material is jammed into this giant K matrix. So we have a 14 by 14 matrix that tells us how hard it is to move every element in X and Y directions. And if you're really interested in like, oh man, I wish I knew more about how that was created, it's just is it the simplest finite element? I don't know. I don't know if it's the simplest, but it's usually the introduction to finite element methods is called the direct stiffness method. And that's what's in this extra FEA material, is how to set up the stiffness matrix, and then also like how to solve and post-process. So we're gonna do the same stuff that's in this extra material, like we're doing part of it, we're just not setting up, like creating the user element and defining like how stiffness affects all this. But you can see like for one, if you think about like one bar, you could move its XY location in both places, and depending on like what angle it goes to, you would have like one stiffness matrix like this. Like this is based on what angles and how everything moves around. So for like that initial like triangle truss, all we did in the homework was just solve for reaction forces, like what are the forces on. But with the finite element, you're getting forces and displacement. So the full, like everything you can know about the problem, at least in terms of solid mechanics. And then coming down, well, let's just run through. So in this case, I'm like setting up this bridge structure. And the thing that we load in is this FEA arrays. It has nodes, elements, and stiffness. So K, LMs, and nodes. The screen is working if it was on. No? It's just me. Why is that the default, that this computer's on and that one's off? Just so I can like talk to myself like a crazy person. All right. This is the single element that I was talking about, of like you can stretch it, kind of move it, and really there's four, like if you think of like a bar, there's four things that you can do with it. You can move this one, you can move the bottom left and right, you can move the bottom up and down, and then same thing, up, down, left, right on the top. But you can't, just like we saw in the homework, you can't just say like, okay, let me apply four forces to it and that'll define how it moved. Because although the forces might add up to 0, like total force is 0, and maybe it's not even, maybe there's no torque on it, but then you end up with infinite solutions where you could stretch it, twist it, and move it anywhere you want. So normally, and this is kind of like an engineering lesson, if you have the choice between displacement controlled and force controlled for finite element, displacement control every time. There's no reason, I mean, like there's definitely boundary conditions that are force. Like it's not that that's never gonna work for you. Usually it works fine, but it's always easier to prescribe displacement than it is to prescribe forces. Because with displacements, you have a big stiffness matrix times all the displacements, and then it equals the reaction forces. It's a lot easier to kind of go that way, figuring out like what force is required to create this displacement. All right, so anyway, so here's like one thing, just stretching a little bit, some reaction forces, and then the thing that I was showing to myself, no one else, is coming all the way down. That same function, save z, that creates that npz file, it's saving the nodes, the elements, and the stiffness matrix. So you can grab that and reuse it for like any post-processing. Let's take a look at nodes. Here we go. And again, this is like a finite element thing. Every finite element process, like when you do all that CAD modeling and stuff, it creates these two things, a node matrix and an element matrix or array, like however you want to call it. But the nodes is like all of your degrees of freedom, so every like corner, and it depends on what kind of element you use. Sometimes there's corners and midpoints, but let's just say the corner. So every corner of your like cubes and triangles and stuff, they all get a location, like their initial location. That's what this is, like a 1, a 0, 0, a 2, a 150, 260. So that's where all the nodes are before any forces are applied. And then this element array is, for this case, every element only has 2 nodes. So like element 1 is connecting 1 to 2. 2 connects 2 to 3, but then 3 is connecting 1 to 3, so we make a triangle and then kind of connect it all the way through like that. And yeah, in the background, this is what every FEA program is doing, no matter how advanced. They always have some node array, some element array about how to define them. As you get 3-dimensional and like higher order elements, you might have, what would that be? 2, 4. What is it? What's a cube? If you have, there's 6 like edges to a cube. So there might be like 10 nodes. If you have 4 nodes for the top of the cube, 4 nodes for the bottom, but then all the midpoints defined within that cube. So you might have like 10 nodes defined in this like element 1 and element 2. Just for fun. And all right, so we got that coming through. Save the work. So there's also like an example of how to post-process these results. It's specific to this one case, like this IX and this IY have to be defined up, coming back up. I know I'm scrolling up and down. It gets defined this way in this extra FEA material. But then we have a nice like post-processed form. Like, oh, we can look at what happens if we apply 0 force versus 10 times the force. And it's all linear. So if it's 10x scale, really that's 10 times whatever load we applied to it. Yeah, so that one's kind of a tour of like background information for this FEA project. That one should be it's either ill conditioned or singular. Yeah. So sometimes singular VOCs doesn't look like they're ill conditioned. It's a stick problem. Oh, it looks like that. Yeah. See, records. So you try to get into the song. Yeah, you have at least two equations that are spread multiples of each other. Yeah, so
No.
okay.
It dropped from like 3 feet and the top came off like open. Not like one of these, like the top disconnected. I just like kept them in my personal bag, so I would like give them hands. But then I did still email them. Okay, what's it? Okay. Yeah. So guys like Wisdom Wednesday will be like hell. And do nothing. No, I think they were saying shakers. It kind of wasn't shakers. Because of my so like so there's this like chocolate and reservoir and there are seals and some way weapons different types of it. Or there is a pizza here. And then these is but the thing is sort of this program is connected and open and a lot of that stuff. What happened? They do not more than like that. Maybe like impressive in 5% part of their contract, or like 5% of material.
For sand. So they want to keep sand on the side.
Yeah.
During one of the other judges,
Yeah, be there. 30.
Can we give them one?
I'll be there, yeah, at the same time Wednesday.
should we go? Yeah.
Post on Wednesday.
Yeah, I presented Wednesday. Nice. Yeah, sounds about right. Do you at least send it to sponsor?
We are going to be, but it's not.
Send me the word in progress so they can say yes or no. As soon as possible.
Then the sponsor is very relaxed. The sponsor is just an extra wishes. Yes. I think that's just I don't think so.
Yeah.
And then went from I think however this I feel like a lot of our I don't know, it's a lot of background, but especially if like a medical project, so I feel like it's important to say the background like every time you present, which is just 400 different people. It's not like common knowledge. Like a lot of teachers stuff, you're presenting with a bunch of like ideas. You don't need to like say
Everyone, she's very helpful.
but like I don't know, I feel like I've seen some close to the background.
As long as it's leading towards, like, as long as the background is sort of the background that you need to understand the solution.
So I feel like all of the work we've done so far is a lot of things. So into different aspects of because you're not what you want to see from what it's with us, your business is going to be like us.
Yeah.
When you buy your own, me too.
Yeah.
that 5 by 5 stiffness matrix when I show right now. But it's just like, okay, we grab the first 4 rows, first 4 columns, and then solve it. And that creates a boundary condition. So it's X5, so that's what this one's doing. So basically, the first value is 0, and the last value is 0. Yeah, well, condition numbers is like a general thing, which is a matrix always has some condition. It's just a ratio. Right now, they're all the same. It's determinant to its state versus exactly how they okay, so it's iron yeah, and like once you have a condition that it's on a long scale issue, all you really care about is it's 100 or 100 million of their breasts. It's like how big is it? It's like a fluctuation like a specific rate. It's just 30. All right, so first thing that we try to do, and again, this is like the best way to impress someone that's having trouble with a finite element project or some kind of numerical methods thing. If there's a matrix involved, just say, did you check the condition of your matrix? Just keep that in your pocket and always pull it out anytime someone's having trouble, because it's a surprisingly advanced question with a very simple answer. Like here, our condition of K, of that K matrix, is very large. 10 to the 17 is a very big number for a computer. So that's one of two things. One, it could be that the problem's very stiff. Like maybe we're trying to solve for displacement of rubber as it pushes up against steel. That's not what we're doing. So there's something else wrong. So in this case, the K matrix defines like stiffness of the entire structure, like the whole bridge, whether or not there are boundary conditions. So there's if you apply forces and try to like solve for what are the displacements, even when force is balanced, there could be an infinite number of solutions. That's why our condition is so high here, because we have just an poorly defined finite element stiffness matrix right now. But what we were talking about was like what is happening here, because I can make the calculation, right? Linalg condition K 2 through 13, 2 through 13, and now condition is 52. That's a reasonable condition number. That's very easy to solve. But what did I do when I said K 2 to 13? Like what is the difference there between the first K and then this K? First, let's just figure out like what does that like bracket 2 to 13 do? Like why am I writing that in there twice? Any ideas? Let's make like a smaller matrix. So if I ask for A 2 to 3, what is this going to give me? 1, 2, 3, 4, 5, 6? or 4, 5, 6, 7, 8, 9, 2, 3, 5, 6, 8, 9. Like what are we gonna get? What's it gonna take away? Or am I doing it? No, 2 to 3. What's it gonna? Yeah, what am I gonna get? 2 to 3. Is it gonna give me rows, columns, a single value? Let's find out. 7, 8, 9. That's why 6 is afraid of 7. Yeah. Yeah.
Like the second right now is 0, 1, 2, and then it's 3.
Yeah, so and this one's a little weird. It goes start, stop, step. So we started at 2 and went to 3, but it won't include 3. It won't include the third row. There is no third row. And then the step size was 1 because it was just looking there. All right. So instead, what if I want row 1 and 2? What would I write there? 0, 2. 0, 2. And I get 2 values. So the nice part about the indexing is that if the difference is 2, you will get 2 rows. So 2 minus 0 is 2, we get 2 rows. 3 minus 2 was 1, so we get 1 row. So that part's kind of nice. We don't get like 2 rows because there's a difference of 1, but it's an off by 1. What if I want 5, 6, 8, 9? How do I get that? There should be a way, right? Yeah. 1, 3, 1, 3. Like this. 5, 6, 8, 9. Good. So in this case, we're doing the same thing. Like we're getting a subset of that K matrix, but we're skipping the first 2 rows, first 2 columns, and then it's length 14. So we're skipping the last row and the last column. And for that, we can't, to really look at it, we'll look up here. That's not helpful. So again, each node, 2 degrees of freedom. So when we skip the first 2 rows and columns, we're saying node 1 in its x direction, node 1 in its y direction are both 0. And then when we skip the last column, we're saying node 7's y direction is also 0. So we're taking a subset of this K matrix and just saying like only solve for these free moving degrees of freedom. So node 2, xy, 3xy, 4xy, 5, 6, and then 7, only x. We can only move left and right, at least from our boundary conditions. And then we can actually solve the problem. At least we can get a solution.
Yeah. What is it? Yeah. Did you print today?
Yeah.
Alright.
Well, because we printed on Friday,
Yeah.
then we have to revise.
Yeah.
Yeah.
Alright. Nice. Oh, so like how much error?
Yes, like,
Oh, why is it revolution? Yeah, or how much error? Oh, I guess how much is that? Oh, okay. What error? Yeah, yeah, I was thinking of the first one, where it's like, you actually can't do it. So, oh, no, that was also the passage was like, how much error? Yeah. So technically, like, if you actually have, like in this case, the inverse does have, it is singular, it would have an extension number, so it should be into the but your computer can't, like, you can't get a matrix in one.
goes away, but it hurts a lot. Oh, that hurts right there.
Well, it's you already healed it. You might be shit out. Oh, I should be. Probably not.
Yeah.
How does it?
Nice to hear.
How much does this is?
It's one, of course, that's the road.
I don't know.
Yeah, exactly.
Maybe? I don't think you tell them. I don't think.
On that one, so the indexing is,
Oh,
yeah.
That makes more sense.
The number of times I've had to tell myself, row column. Yeah. Yeah, so, and now the same thing versus row columns.
Well, they probably, five.
Yeah.
And you probably get one color. How much is this? I feel like a body is like 25 or something.
Yeah,
You made on your genuine like healthy 45 will drop down cardiac arrest because you sleep such a intensive motion where you're shifting your body weight, you're moving really heavy stuff above your back.
Running down the world is travel right is the lower and that stops going. You would say yourself, would be so always
That was pretty candy.
So this is something never hurts to kind of look at it again. It's like when you have a matrix, at least NumPy, MATLAB, Julia, like I think most programming languages use row then column. I'm like 99% sure that it always goes row then column. So if I look at row 0, column 1, then I'm coming in here to this row and looking at the first column, so I should get a 2. And sure enough, I get a 2 because that is like that value. And then row 1, column 2, go down to the second row, all the way to the end, to that last column. So if I'm asking for like 1 to 2, 1 to 3, and 2 to 3, maybe I have to put it in brackets. I don't know if this will work very well. It doesn't like it. How do you set that? Maybe range? That worked. At least if you want to like set up input and then grab. So it went rows 1 and 2, or sorry, 1 and 2, and then columns 2. So just that 6 and 9. Yeah, it always goes row, then column. All right.
Can you check like how many digits are in a number?
So what is this?
Yeah.
Where do you think we could find out here?
Oh wait, where'd it go? I'm gonna scroll down to this definition for conditions and errors. So the first thing that we're asked is like, can we solve this problem? And for the general kind of K matrix, it's not really a solvable problem, but we want to quantify how much error, like if someone just said, I don't care, just solve it, just give me an answer, then we need to quantify like how much error there is in that. So the general formula that we have is like the rounding error is this 10 to the power of the condition number. So that one we have. It's like 10 to the 17 and 10 to the, I don't know, whether you want to call it 10 to the 0 or 10 to the 1 or 10 to the 2. It's halfway, kind of halfway between the two. But then T is how accurate everything is. So in the past, we used 10 to the negative 16, I think. But if you want to find out, if you're like, well, what is the limit for my computer? NumPy has an finfo command, and it's the limits for your given machine, or for like this kind of version of NumPy. There's always like every programming language will have something kind of like this. So if you're looking for, usually this machine epsilon is the number that you're looking for, like how much accuracy do I have when I'm doing math on things, because that's what we're doing. Like linear algebra is a whole bunch of like addition, subtraction kind of steps. And at least in this case, it's telling us 2 times 10 to the negative 16. But we can check it. I think we say float and then dot EPS. Yeah, and sure enough, 2.22 E negative 16. So at least accuracy for most of this stuff is going to be negative 16, that number that we're looking for. But now you can always go and like find it. Usually, at least for 64-bit machines, it's always this number, like 2 times 10 to the negative 16. If you happen to be on a like an old school 32-bit machine, it'll be different. I think we can actually ask for it. Float 32? No. I think there's an option. No, data type. Int 32. Yeah, there should be a float 32. Floating? Looks like we don't have a float 32 anymore. There's only float 64. I mean, it makes sense. Nobody uses 32-bit numbers anymore. I'm just surprised that it's gone. (32-bit) integer. So you can do 32-bit integers, but not floating point numbers. Strange. Okay. So anyway. And reason for that is like, let's call this like my EPS. Oh, it froze. Or maybe it really doesn't want to add 1 to that machine epsilon. It really doesn't want to do that. Oh, it worked. Yeah, if I try to add 1 to that epsilon, I get a change. So some small difference. And if I do it a whole bunch of times, it'll be bigger. So here, I can keep adding that machine epsilon. It's like this, it's small, but it is a number, versus if I just divide by 2, where it's, now it's 1.1, it's not a huge difference. This should divide in half, like this should be a 11102 at the very end, my 1, but instead, oh, where'd it go? Yeah. Instead I get just a 1. So I'm adding it, but it's not actually, I can't keep track of that addition because the number is too small. So that's why this machine epsilon is sort of like our accuracy when we talk about like how we store numbers in our computer. Cool. Last second questions. Good luck with oral 2, yeah, number 2. Halfway there, just 2 more to go.